Section 15.3, Conservative Fields and Independence of Path. Okay, so let's start with the fundamental theorem of line integrals. All right, it goes like this. Let C be a piecewise smooth curve lying in an open region R. Let C be piecewise smooth path in open region R. Okay, given by R of t equal to x of t in the I direction plus y of t in the j direction for t between a and b. Okay. Then if f of xy, our field, our vector field, is equal to m in the I direction plus n in the j direction, is conservative. Okay, meaning the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, remember that, is conservative in R, and m and n are continuous on R. Then the line integral over C of f dotted with dr is equal to the integral over C of the gradient of f dotted with dr. These are all vectors there. Dotted with dr is equal to f of x of b, y of b minus f of x of a minus y of a, okay, where f is the potential function of our vector field f. So this is very good news for us if we are trying to calculate the integral, the line integral, for some function that is, some vector field rather, that is conservative. Because all we really have to do is evaluate our function at t equal to b and subtract our function at t equal to a. So we're just taking the end of our function, and it's, goodness sakes, what I'm trying to say is it's like evaluating our integral at the bounds of integration, right? We take the higher number, the right-hand side of the interval, we plug that in, and then we get our lower integral and plug that in. And that is because f, our vector field, is the gradient of the potential function. So the antiderivative is already known if we have the potential function. So that's a really, really cool result, and it's something that we're going to be able to use to help us get through this section more easily. Another great theorem in this section says that the conservative vector field allows us to take an integral along any path. It's independent of the path that we choose. So if our vector field one more time, there we go. If our vector field f is continuous on an open connected region, okay, then the line integral over C of f dotted with dr, okay, is independent of f. I'm sorry, is independent of path. Independent of path C if and only if f is a conservative vector field. Okay, so we could come up with, suppose I've got point A and point B here, and I want to perform my line integral. If f is a conservative vector field over this space, then whether I go from A to B directly with a very simple line, or whether I do some kind of crazy, almost exponential looking curve to get to it, doesn't matter. I don't need the whole thing there, do I? Doesn't matter. It's going to be the same either way. So it is independent of path. I can go there any way I choose. However I choose to make my path is entirely up to me, and it does not matter because it will take me there either way. And that in that integral, that line integral, is going to give me the exact same value either way. So let's go ahead and do a couple of examples so we can see these guys in action. Okay, so let's find the work done by the force field. Given by f of xy equal to 1/2 xy in the I direction plus 1/4 x squared in the j direction on a particle that moves from 0, 0 to 1, 1 along the path darn it, C1 equal to y, C1 equal to, no, C1 being y equal to x, and C2 being y equal to x squared. Okay, so according to the fundamental theorem, if this is a conservative field, then all I really have to do is find my parameterization for C1 and for C2, and then just evaluate my potential function at 1, 1 and at 0, 0. So let's see here. First of all, we have to verify that f is conservative. Okay, so let's do that. So f is conservative if we take our second partial derivatives, or I say that, second partial. If we take the partial derivative with x of the y component and the partial derivative of y with the x component, and it comes out the same. So m is equal to 1/2 xy, my is equal to 1/2 x. N is equal to 1/4 x squared, n with respect to x is equal to 1/2 x. So these are equal, therefore this is conservative. So we can just use the fundamental theorem to calculate this. So to do that, we need to know, well, what is the potential function? Well, we know that, let me get a brighter color. We know that f being equal to 1/2 xy in the I direction plus 1/4 x squared in the j direction is actually equal to the gradient of f, so we can integrate each of these. So I'm going to integrate 1/2 xy with respect to x, and I'm going to integrate 1/4 x squared with respect to y. Okay, so this is going to become 1/4 x squared y plus possibly some constant function of y. And then here, if I integrate with respect to y, I get 1/4 x squared y plus possibly some function of x. Okay, so since there are no terms in either of these functions that are exclusively x or exclusively y, both of these are 0, both of the things here are 0, and so our potential function f is equal to 1/4 x squared y. And again, you can verify that that is accurate. Take the partial with respect to x, you should get m. Take the partial with respect to y, you should get n. And we do. Okay, so we need a parameterization for this. So we are going from the point 0, 0, let me put a circle around that so I don't lose it. We're going from the point 0, 0 to the point 0, 1, and we're beginning this with, let's do the first one. So for C1, we've got y equal to x. Okay, this is a pretty straightforward parameterization. We've got r of t is going to be equal to t, where t is between 0 and 1. Okay, so pretty straightforward there. We're going from 0, 0 to 1, 1. Ooh, I wrote 0, 1. That is not what I meant to write. 1, 1. There we go. Okay. All right. So there's that. Then all I have to do is take my f of x, y equal to f of x of t, y of t, and evaluate both of those from 0 to 1. So my integral over c of my vector field dotted with dr is going to be equal to, by the fundamental theorem, f of x of 1, y of 1, minus f of x of 0, y of 0. Okay, well, x of 1 is just t, which is 1. So x of t is t, so x of 1 is 1. So this is going to be 1/4 times 1. And then y of 1 is 1, so times 1. So we've got 1/4 x squared y, so 1/4 1 squared times 1, minus, and when I plug in 0, I get 0 for x and for y. There we have it. So this is going to be equal to 1/4 minus 0, or just 1/4. There we go. Okay, now, because this is a conservative field, we know that it's independent of path. It will not matter what path we take. So let's do this for our second path then. So for this, we were using y equal to x squared. We need to go from the point 0, 0 to the point 1, 1. So r of t is going to be equal to, let's see if we can find this. Yes, I believe we can do t squared for this one. So y is equal to x squared, x is t, y is equal to t squared. Okay, the potential function is the same as before. We already found that. So that was 1/4 x squared y. Okay, now according to the fundamental theorem of line integrals, all I have to do is evaluate this at x of 1, y of 1, then subtract f of x of 0, y of 0. Okay, so this is going to be f of x of t, y of t. It's going to be 1/4 t squared times y is t squared. Okay, so evaluating this at 1, so our t, of course, here I didn't even write it down, but t is between 0 and 1. So evaluating this at 1, we get our integral is equal to 1/4 times 1 squared times 1 squared minus 1/4 times 0 squared times 0 squared. So once again, we get 1/4, and it's independent. So we didn't even have to do any work here because we knew that the function, the vector field rather, we knew that the vector field was conservative. So it doesn't matter what path we take. So the goal here then is for us to find the nicest, simplest path we can to get us from point A to point B. Okay, let's go ahead and do one more example. Okay, so let's find the work done to move a particle from point 0, 0 to 0, 2 in the vector field f of xy equal to y cubed plus 1 in the I direction plus 3xy squared plus 1 in the j direction. Okay, so if this is a conservative field, we don't have to worry about a path. It's going to be independent of path. So first thing you always want to do is verify it's a conservative field. So we've got m equal to y cubed plus 1, n equal to 3xy squared plus 1. Partial with respect to y is 3y squared. Partial of n with respect to x is equal to 3y squared. So these are equal, therefore it is conservative. Conservative. Okay, so that means it doesn't matter what path we take. So we can come up with any path we want. I don't want to go too far off the screen. So there's my x, there's my y. We're beginning here at 0, 0 and moving up to 0, 2. Okay, so we need a parameterization for this curve. So r of t is going to be equal to, well, the x component doesn't change, so that'll stay 0. The y component, maybe it's 2t, and we'll let t be between 0 and 1. I could have said let t be between 0 and 2, and my y component would have just been t. It's totally up to you how you parameterize this, just so long as it does take you from 0, 0 to 0, 2. So t here is between 0 and 1. There we go. Okay, so there's that. Now, it's a conservative field. I can find the potential function, use the fundamental theorem of line integrals, and boom, we're done. So let's do that. Let's find our potential function f. So that's going to be the integral of m with respect to x, which is equal to the integral of n with respect to y. Okay, so if I integrate m with respect to x, let's see. What was m? Let me rewrite these so I can see them. So that's y cubed plus 1 dx. That's going to be equal to the integral of 3xy squared plus 1 dy. So let's integrate both of those. So that's going to be y cubed x plus a possible function of y That's going to be equal to, now we're integrating this with respect to y, that's going to be xy cubed plus y plus possibly some function of x not containing any y's. Okay, and if we put those together, what do we get? We get that our function f then is equal to y cubed x plus y. Okay, so this is going to be this function of x, so that's just x, and this constant function, the function of y that doesn't contain any x's is going to be equal to y. That'll keep these equal. Now, then as before we saw, it could potentially have some constant c, but do we need that? Do I need to know what that is? How would I find it? I have no idea. I'm not given any information about this potential function, what its function values are, no initial conditions, nothing. However, this is a definite integral, right, that we're taking, and we are subtracting our function value at the endpoints. So that c is going to disappear anyway, so we don't even have to worry about it. So I need f of x of t, y of t. So x was equal to 0, y was equal to 1. No, that's not right. What was y equal to? 2t, there it is. Okay, so x was 0, y was 2t. So this is going to be 2t cubed times 0 plus 0 plus 2t plus a constant, right? So we're going to evaluate this at the endpoints. So our integral over c of our function dotted with dr, our work done, that's going to be equal to 0, 0, okay, 2t evaluated at the endpoints for t, which were 0 and 1. So we put that in, that's equal to 2 times 1 minus 0 is equal to 2. And we're done. We didn't have to do anything wild, nothing crazy. Nice, fun, straight, simple. Dealing with conservative fields is very, very nice. Okay, so one last theorem I want to give you, and then we'll wrap it up for this section. So this is equivalent conditions theorem. Equivalent conditions. Okay, so let's go through all the preliminaries here, all of our conditions that have to be in place. So we've got to let f of x, y, z be equal to m in the I direction plus n in the j direction plus p in the k direction. Okay, it's going to have it's going to have continuous first partial derivatives. Okay, and that's going to be in an open connected region R, in an open connected, connected region R. Okay, and we're going to let C be a piecewise smooth curve in R. Okay, then the following are equivalent. Number 1, the following are equivalent. The following are equivalent, so you know what that acronym is for. F is conservative. Okay, so that is that f is equal to, gotta remember to put my vector symbol there. So f is conservative, so it's the gradient function of f. 2, the integral over c of f dotted with dr is independent of path. Okay, so that's what we just saw a few moments ago. And finally, 3, the integral over c of f dotted with dr is equal to 0 for every closed curve C in R. For every closed curve C in R. All right, so very interesting there. Okay, all right, that's going to be the end of this one. If you guys have any questions about this while you're doing the homework, do please let me know. I'll get back to you as quickly as I can. And yeah, getting close, getting close.